Thank you for having me. I'm going to be talking about quantifying and modeling brain organization. So first, I'll give a brief introduction to how you quantify brain organization and why it's beneficial to model it. And then I hope to give a very basic outline of generative modeling methods, specifically what the model is doing and how it's doing it. And then I hope to have a little bit of time at the end to talk about ways in which the model has been applied in the past. So first, if you're familiar with graph theory, please ignore me for the next 2 minutes. I just want to make sure that we are all hold on. Uh-oh.
You choose.
I'm going to go with close and then try and just restart it. Okay.
Try to click on it again.
Yeah, it's opening up, I think, all of the other presentations that were here today.
Oh, that's not good. Anyway,
Can
maybe
I
just close them one by one.
Yeah. Oh, I think that was mine. Okay.
Okay, test.
Okay, I think we're back. So first, an introduction into what we're talking about today. Oh no. It doesn't seem to be working.
Save it as a PDF. Present it as a PDF. I mean, I'm assuming it's something on the animation that makes it crash.
Yeah, that's probably true.
If you can open it and save as PDF, maybe it's the best I can suggest. Apart from switching off and on again.
I could also try and just skip this slide, maybe, because I think it's
Okay,
the
yeah,
animation
maybe-
on that slide.
Maybe that's a quicker option.
Okay.
Is it going to do the trick again?
Okay, we're skipping a slide, but essentially what we're talking about today is a network of the brain where the circles are indicating regions of the brain and the lines between them are depicting connections between them, which could be structural or functional. And how we quantify organization is by applying graph theory. This can be both global and local measures. Global measures are simply a single metric for the entire network. For example, you can see that this example network has 3 distinct modules, so we can actually quantify how modular the entire network is. We can also quantify global efficiency, which is related to being connected by short path lengths. There's also local measures, which are per region. So for example, this region is highly clustered with regions around it, so that region would have a higher clustering coefficient than, for example, this region would. Similarly, there is the measurement of degree, which is simply the number of connections that region has. So this region has a degree of 4, whereas this region has a degree of 2. And I don't have time to talk about it in depth today. There are many more measures than just that, but if you're interested in learning more, these are some really helpful papers. And of course, there's lots of different toolboxes in MATLAB, R, and Python to help you apply graph theory to whatever your network might be. The reason why this is important is when we look at the organization of the brain, we find that people's brains are organized differently. And the difference in organization is highly related to different cognitive and behavioral outcomes that we see. And so an important developmental question is, why are people's brains organizing differently to others? And there's a very helpful quote from a review article that says, brain organization is shaped by an economic trade-off between minimizing costs and allowing the emergence of adaptively valuable topological patterns. Essentially what this means is that if our brain was organizing simply to minimize cost, our brains would be completely made up of short-range connections, because long-range connections are more metabolically costly to make. On the other hand, if our brain wasn't at all considering cost, we would have, for example, a large number of very long-range connections that might be valuable to the topology of the network. But we don't see either of those two cases. We see that there's a balance between the two. Our brain seems to be organizing in a way that both minimizes cost, but also allows for the emergence of adaptive topology. And this is hard to look at in an actual brain because we aren't able to actually look at the economic constraints of a brain through a scan. We're also typically limited by having a single screenshot of a scan that someone might have undertaken. Of course, there are longitudinal data sets, but we're usually limited to cross-sectional data. And so it's hard to look at how organization is changing over time. And so this is where modeling becomes very helpful, because we can actually generate a simulation that grows over time. And if we match that simulation really accurately with an observed network, we then can get some information about how that network might have emerged, because we do know the economic constraints that our model was grown under. So that was the very brief introduction, and now I'll get into generative modeling methods, specifically what is the model doing. So for generative network models, we provide the model with all the regions of the brain which we use from a parcellation, and importantly, we know the distance between these regions. And a lot of researchers will also include a few sparse connections, for example, these red connections, which would be calculated from being present in the vast majority of their sample. And then what the model is doing is it's adding connections in unconnected nodes over time until it reaches the size of the network that it's trying to simulate. And how it's adding connections is first it's calculating the probability of all potential next connections, and then out of those probabilities, it's selecting one, again, probabilistically, and it repeats that over time. And so there's an equation that allows us to quantify the probability of a connection being added. In 2012, Petra Vertes from the psychiatry department tried a variety of different equations to quantify what the next connection might be. And through her work, she determined that this bottom equation was the most accurate for simulating human networks. And so I'll break down what this equation is, because it's actually a fairly simple concept. Essentially, this equation is determining P, the probability of two regions connecting. So for example, in this network, it could be A and B. And that is a trade-off between the cost and the value of that specific connection. Cost, as I've been mentioning, is related to distance, because the longer range connections are more metabolically costly to form. And so this equation is going to penalize long range connections. And for value, as you can imagine, could be a variety of different things. Specifically, Betzel in 2016 tried different ways to quantify value. For example, regions could preferentially connect with other regions that are highly clustered, or maybe they're connecting with other regions that have a high degree. But what Betzel found in 2016, and many have since also found in different neural models, is that homophily seems to be the best metric for simulating neural networks. Homophily essentially is related to having similar connections. So as you can see, A and B both are connected to a third region, and this means that they're more likely to connect than if they didn't have this connection in common. So essentially, regions are preferentially connecting with other regions that are similarly organized to themselves. So that is broadly what the model is doing, and now I'll get into how we actually use it. So for this cost-value equation, both metrics are raised to a predefined parameter. For cost, eta could be something realistically between -3 and 0, and what's important here is that eta is always negative, and this is how we preferentially select against those long-range connections. For value, this is raised to gamma, which could be realistically between 0 and 1, and this is essentially weighing how important value is to the formation of this specific model. And so we can plot this out with the cost parameter on the x-axis and the value parameter on the y-axis, and we can pick out different parameter pairings to grow simulations from. So for example, if we grew a simulation from this area, the parameter space, this would be highly constrained for both cost and value. Whereas if we grew a model from this parameter pairing, which is low constraints for both cost and value, the second model would be a little bit closer to a randomly organized network. We could also try a strong value parameter and a weak cost parameter, which would mean this model would be driven more by selecting for topological value than cost minimization. If you remember from the introduction, it would look closer to this. And the opposite being from this bottom left-hand corner, if you have a strong parameter for cost and a weak parameter for value, it would be strongly driven by cost minimization, and thus slightly closer to a network that might look like this. So essentially what we get is different quadrants that have different economic constraints for our models. And so what we want to do is we want to try a variety of different parameter combinations throughout these different economic areas. There's two different methods for this parameter selection. First, there's grid search, which is a determined method, where we essentially equally distribute our models throughout the parameter space. If we increase the number of models we run, we simply decrease the difference between the parameter pairings. There's also the Voronoi tessellation, which is a random sampling method. Essentially, it picks out random parameter combinations in our parameter space, and the areas that are performing well, which I'll talk about in a minute, will be preferentially selected more. So for example, if this area is having parameter combinations that fit very accurately, there'll be more parameter pairings selected from that region. In either scenario, what we end up with is a large number of different simulations that were all grown with slightly different parameter pairings. For example, let's say we ran 10,000 models. The next step will be to look at our participants in whatever sample we're interested in, and we want to find, out of those 10,000, what is the best fit model for each individual. So we go through all of these simulations and we compare them to each participant. What we're comparing these two networks on is their organizational properties. So we use something called the energy equation, which uses the Kolmogorov-Smirnov statistic on 4 different local organizational properties. So if we just look at one of these, let's look at the KS statistic for degree, for example. What this is doing is it's taking one observed network, so for example, participant 1, and one simulated network. It could be, for example, 236 out of our 10,000, and it's comparing these on this metric, specifically degree. And so we could plot out the frequency of degree, which, as if you remember from the beginning, is a local measure that will have a measure for each region. So we have, if we were using a parcellation of 90, we would have 90 measures per network. And we want to compare these two networks. And how the KS statistic does this is through the cumulative distribution function, or the CDF. For those of you who aren't familiar with CDF, essentially it looks at the probability of selecting out a certain number as well as everything previously. So for example, for 7, it's what is the probability of selecting out 7 from that distribution or anything less. For this, looks like it's around 36%. And so it plots out the CDFs for both the observed and the simulated networks. And what the KS statistic is doing is it's finding across this distribution where is the maximum difference between these two CDFs. For this example, these are actually fairly accurately fit networks, so maybe the CDF would be something like 0.3. And so what the energy equation is doing is you go back to the energy equation and you plug this metric in for degree, and then you repeat this 3 more times with the 3 other local organization properties. And so for this example, the energy would be 7 because that's the maximum difference for this equation. So essentially what this is energy is a way to quantify the maximum difference between the observed and the simulated networks on these 4 different properties. And so what we end up having is every comparison has a different energy metric. And so we can plot this out back in our parameter space where we plot every energy for each parameter pairing. Here you can see in the darker regions are the lower energy models, so essentially the better fit models. And we can actually plot out where the best fit models are. These white dots are indicating the best fit model for a diverse sample of infants. These infants were born premature and at term, and so they're organized very differently. And what we find is despite the fact that our observed networks have very different organizational properties, they're simulated in a very narrow parameter space. Essentially what this is showing us is that very minimal differences in weighing, cost, and value are yielding extremely differently organized networks. And what we find through this work as well as many others is that even though this equation is very simple, just the cost and the value of every connection, most of the researchers out there are finding that energy is quite low for these fits. So these models are being fit typically with an energy of 0.2 or below, which is quite impressive given the lack of information that the model gets. And I think I'm getting close to time, so I'm just going to wrap up with a few ways the model has been applied in the past. These top citations are different researchers that have used the exact same equation that I talked about today. And these bottom 3 are examples of people who are also doing generative modeling but with slightly different equations. But what we find is that we can relate the cost and value parameters to a variety of different situations. For example, we can see that across age, the cost parameter is significantly changing. This is not found for the value parameter. So it seems as though the networks are basically weakening their preference for cost minimization over time. But of course, this is cross-sectional data, so take from that what you will. But we can also see, most importantly, that this works across scales. So today I've been talking about the macro scale organization of the brain, but people have also looked at this at the cellular level, and they see the same results of homophily being the most accurate method for value. People have also looked across species. So there's models of mouse models looking at different adversity metrics and finding that if the mice that were exposed to adversity early on in childhood, or early on, I guess it's not childhood, but early on in development, typically have less constrained models and thus slightly closer to a randomly organized network. But yeah, we find lots of really interesting results. So if you're interested in learning more about the model, I'm definitely interested if you want to reach out. Thank you.